Welcome to helpyourmath.com. In today's video, we're going to be exploring the cases of domain exceptions. Now, there are many times where you have domains where they have no exceptions, and mainly one of the main domains that we know have no exceptions are polynomial functions. And as we can see here, all polynomial functions have no domain exceptions. This means that all real values work for the domain, meaning we can indicate the values of the domain in interval notation would be negative infinity to infinity. And the reason for this is simple. If I plug any x value into the function of a polynomial, I get an exact y value. And until the case I get something that I'm inserting and I get an undefined value, the domain exception doesn't exist for all polynomial functions. So if I have a polynomial function or a linear function, I can insert all values of x into these and get a y response. And so for this reason, all polynomial functions have no domain issues, meaning their domain would be negative infinity to infinity. Here we have an example of that, right? And in this case, to explore the example, I'm going to substitute a few values in for x to show you guys that for every input that I have an exact output. So we'll start off with f of 4. And I'm picking 4 just as an arbitrary number because there's really all numbers will work for this function since it's a linear equation. Even though you see a fraction, if the x isn't in the denominator in the fraction, we won't have the domain exception. And so if I insert 4 here, I get this, which is 12 minus 1/6. Now, this just becomes 11 and 5/6. Right? And this is an exact value. This is a real number. And we see here that the value of f of 4 is 11 and 5/6. This could also be written in a decimal format or even just like an improper fraction, which would give us 71/6 if you did the long work to solve it, right? Now, moving on, let's try a negative number to see if it works the same on the negative side for this. And f of negative 4 then would be 3 times negative 4. And this is then minus 1/6. And this becomes negative 12 minus 1/6, which is negative 12 and 1/6. Which, if we made this an improper fraction, would give us negative 73/6. We can even insert the 0 in here. We get 3 times 0 minus 1/6, which is 0 minus 1/6, which produces the value of just negative 1/6. So for each x value, I get a y value. And for this reason, the domain is all real numbers because each x creates some form of a y. And it's a unique value of y, and for that reason, the domain for all polynomial functions are all real numbers, which is negative infinity to positive infinity. All right? Well, now that we got that out of the way, this is all the formal knowledge you need to know before beginning your domain exceptions. We'll begin with our first case of a domain exception. And the first case is the rational function, which I like to notarize as the denominator of x in a function. This way we could identify with the piece of the denominator as a function separate to the actual function. And the way this works is pretty simple, right? And so in our first example, what we're going to do is we're going to take the problem f of x is equal to x plus 5 and x minus 7 in the denominator. And the way this works is whatever the denominator is, we understand that in a rational expression, if you're dividing by 0, you get this undefined value. And for that reason, the denominator of x cannot equal 0. So to solve your domain issue, for any case where you have a rational expression, our first step is simply taking the denominator function, which is right here, x minus 7, and setting it not equal to 0. Once we do this, we just have to solve it to get our domain exception. So our first step is going to be to add 7 to both sides. When we add 7 to both sides, the left side 7's cancel. We're left with x cannot equal positive 7. Now to put this in interval notation for the domain, we say the domain of f of x is x belongs to, and here we see that it's all values except for 7. Usually most professors allow this to be the domain, just x cannot be 7 as the exception, but in interval notation we'll put negative infinity to 7 without including the 7, right? This is what the parentheses does, union 7 to positive infinity. Now this excludes the 7, and it's all values except for the exact value of 7. And that's the first case of the rational function, which I termed the denominator of x. And in this case, we see that x is all real numbers except for the value of 7, all from negative infinity to 7, and all from 7 to positive infinity, excluding the 7 itself. Let's move on to case 2 now. Now in case 2, we're dealing with something a little bit different, right? Case 2, instead of being a rational expression, is going to be a radical one. And to see that, what we're going to use is, instead of the denominator of x, we're going to use the radical of x, right? Which is the square root case. Now, in this case, call this the radical functions. This is termed r of x. And here our example will show we're taking the square root of some function inside the square root. And in this case, the r of x function inside the square root must be greater or equal to 0. The reason for this is we can't take the square root of any negative numbers, right? And if we did try to take the square root of a negative number, what we get is an imaginary term which does not exist. And so our exception here excludes all the numbers that are outside of the range of when this square root is 0 or greater. And so we set the inside of the square root greater or equal to 0 to solve that value. So here's our example for this case. We have the r of t is equivalent to 9, take away the square root of t, take away 2. And in this case, we see we have our expression of our little r of t. And we see here we have our actual problem. 9 take away the square root of t minus 2. And here we know that our radical function is the inside of the square root, right? So we're going to say t minus 2 is greater or equal to 0 to solve our domain. And again, we do what we did in the last problem. We just solve our inequality here, and we're going to add 2 to both sides to do that. These 2's on the left cancel out, and we have t must be greater or equal to positive 2. And now to turn this into interval notation, we're observing what it says here. And it says all values including 2 to infinity are valid for input into this function. And in fact, all values that are greater or equal to 2 will produce a value of y for every time we insert it. So our domain for this function, this is the r of t. Domain of the r of t would be based on the t variable. So t belongs to, and in this case we're not going to use an open parenthesis because open parentheses exclude a value. Here we're including the 2, so we're going to use a bracket. We put 2 to the value of infinity. And this is the domain of the square root expression of 9 take away the square root of t minus 2. We have 2 to infinity. All right, and this covers case 2. So every time we see we have a square root, remember the inside of the square root must be greater or equal to 0. Don't confuse this by setting the entire equation equal to greater or equal to 0, because then what you'll be solving is first a 0 and all values that produce positive values of the function for y. And we're not looking for that. We're just looking for which values we can insert into the radical without causing it to give us an undefined value. Now, there are other cases that we deal with, but mainly these are the 2 major ones that we have to confront every time we're doing work. And because of that, what happens is we get a combination of cases. And so case 3 I like to call the radical / rational expression. And this can happen in more than one way, right? So I'm going to show you guys 2 different ways in which it can happen. The first case, what we're going to deal with, is a basic one. It's the case where our function actually just has a square root in the denominator. And I like to coin this one as the function of drx, right? A denominator that has a radical in the denominator. And so in this case, very similar to the rational expression, we know that the denominator cannot equal 0, right? So we know our dr of x cannot be 0. And we also know that when we deal with square root functions, the inside function must be greater or equal to 0. And now if you're dealing with both of these cases and they both have to work with each other, and we know that this cannot be equal to 0, and this also must be greater or equal to 0, our result for these two combined will have the denominator then must be just simply greater than 0. If it can't be 0, but it has to be greater or equal to 0, then it just has to be greater than 0. So this is our exception case here for all values that will be part of the domain. And we'll exclude everything that's counter to this argument. And so now, let's take a look at one of these cases. And what we're going to do here is we're going to put a very basic problem, very similar to the one we did previously, simply because there's two things we have to worry about here. Now we know that when something cannot be 0 and must be greater than or equal to 0, it's just simply greater than 0. And so here we're just taking the inside of the denominator of the radical function and we're just setting it greater than 0. And again, we just go on to solve this problem. We take the x minus 7, this inequality, and we solve to get the domain. We add 7 to both sides. These 7s will cancel and we get x being greater than 7. Now that we have our rule for what domain values actually work for the function, the rest are the exceptions. We say the domain of this function is x belongs to all values that are greater than 7, right? Now if we think about that, that means 7 is not included. So we have to use a parenthesis to exclude the 7 and take this all the way to infinity. And we know it's going to positive infinity because of the direction, right? And that covers the radical rational function part 1. In the second case, it's a bit more complicated when we have two components that we have to deal with. And namely, the difficulty in this problem is going to exceed a little bit of the expectation as you might imagine this might be. And the reason for it is whenever we have a radicand expression in the numerator and we have a denominator expression in the denominator, what do we do in this case, right? So in this case here, what we'll do is we'll make the numbers a little bit more interesting. In this case, we'll say the radicand function must be greater than 0, greater or equal, and the denominator function cannot equal 0. And if these two contradict each other in any way, we're going to have to compile the domain of both of these collectively. And what I'm going to do to illustrate that is I'm going to draw a number line of x where we see what they have in common and what we'll take with us. Because I feel like it's the easiest way to understand it analytically and visually. So we'll give that a go. And here now we'll have the function of x being the square root of 5 minus x over, we'll make this a positive 2 here. All right, so let's see if we can follow the rules real quick. Now we know for our exceptions here, we know that the square root must be greater or equal to 0, while the denominator cannot equal 0. So let's put both of those rules down. We have 5 minus x must be greater or equal to 0, and the denominator of x plus 2 cannot equal 0. So now let's start with the left one, and we'll take the 5, take away x greater or equal to 0. And we're going to subtract 5 to both sides. These will cancel. We have negative x is greater or equal to negative 5. And a cool trick I like to do when I see something like this is whenever I change all the signs of the functions of the problem, I also change the sign or the direction of the arrows. This way, when we have a positive x, we know it will be less than or equal to a positive 5. Now many people don't like to do this, so I'll show the division method. Whenever you divide both sides by a negative term, arrows will change directions, right? So this is going to go from the right to the left. This becomes a positive x, and this becomes a positive 5. And so the first domain we have is x is less than or equal to positive 5. In the second case, we have x plus 2 cannot equal 0, which we subtract 2 to both sides to solve. The 2's cancel on the left. We have x cannot equal negative 2. And so we see there's a bit of a contradiction here because all values less than 5 includes negative 2. And so what we're going to do here is we're going to first graph x is less than or equal to 5. And what we have here then is the number line going to negative and positive infinity. And the first stop we have is in the middle for 0. Then we have this value of 5, which has a solid dot. And the reason why it has a solid dot is because it's included. So I'm going to put the bracket for its inclusion for 5, right? The second value we have is negative 2, which is on the counterpoint over here. So here we have the minus 2. And it has all values except for minus 2. So this is actually going to take an open dot. Now, the 5 goes from 5 to negative infinity, so we're going to bracket that in. And the 2 goes for everything except 2, which takes 2 parentheses at its ends. Now, to compile this domain then for this function, once you do this visual, it makes it very simple. So the domain of f of x is then, you take the values you see, and we see that the domain of x belongs to, and this is what the e means, this little e with the little pitchfork sideways, that means belongs to. And we take the negative infinity with its parenthesis. We put the comma, and we're going to add the negative 2 in a parenthesis on this side and this side. And we're going to unite this with the other side of this. So it goes from negative 2 to positive 5 with a closed bracket. And that's the domain of the radical rational function, part 2 of it, right? So that's kind of case 3 and 4 combined together. Thank you.